In this episode, we're going to do something very, very fun I've never done before. It's going to be cool. We're going to build a static RAM tester with a Raspberry Pi Pico. So this project came from an idea. I was trying to fix some boards.
Once we have it all wired up,
circuits that use
like this.
A flash memory that works like static RAM. And the problem is the static RAMs often go bad, and so did some other parts of the circuit. And the process of testing the board is kind of a pain. It takes a long time. So I was trying to figure out ways. There's ways I can narrow things down, but one of the problems is often the flash RAMs are bad, and I don't have any tool to just quickly test that. And that would streamline my life if I could just test all the RAMs and throw out the bad ones. And I've also been itching to try out this Raspberry Pi Microcontroller. I haven't done anything with a microcontroller for probably 15 years when I was just playing around with it, some hobby stuff. And I wanted to try this Raspberry Pi Pico microcontroller. And I was wondering, hey, I wonder if I could use this to test the RAMs. So being that this RAM, this flash RAM has a weird voltage situation that I can't provide the voltages for yet. But I was thinking, hey, I got a static RAM laying around. It should be more or less the same. Let's try that. And so I built this little board to test the static RAM. And I actually can use this because sometimes these static RAMs go bad on like Galagas or Galaxians and things like that. But I decided to build this board as a proof of concept, and it worked. And I was really excited about it. So I thought I'd share this with you as a video. So this is the board. I have a Radio Shack. Remember them? They were a company that existed once. Universal breadboard that was laying around from 15 years ago. And I had this Raspberry Pi Pico, so I plugged that in, and I have a static RAM here. This is a 74S201, which is a 256-bit static RAM. 256 addresses, each address can hold 1 bit. And if I remember correctly, these guys are used in certain games like, I think Pac-Man uses them. No, maybe they do. Galaxian uses them, I think, and I want to say Centipede does too. But I also don't have an easy way of testing these. So this was kind of cool. Anyway, so we have those parts. And then all I really need is I need some power. But we're going to get power through the USB. And I have some LEDs and resistors. And those are going to be used to visually signal. I have 3 tests that I do on the RAMs. I do an all 0 test, an all 1s test, and then random test. So I have 3 LEDs to show the display. The computer will also display whether the tests have passed in the console. And then, of course, I have jumper wires. So there's not much to this. All I have to do is figure out how to wire this thing up and then write some code. And as well as figure out how the static RAM, the timing of it. And I don't do anything really complex with the timing. I just make sure that I do things in the right order, basically, in this case. It should be also mentioned that technically these guys are not the same logic level type equipment. The Raspberry Pi Pico goes from 0 to 3.3 volts. And the other chip is a TTL chip from 0 to 5 volts. However, the Raspberry Pi, when it 0 is a 0, and when it puts out a high signal, that's 3.3 volts, which is well more than the cutoff for a TTL chip, which is a positive, signal. So that should work as actually inputs, and we will have to have the 5 volt power, but we do have that from the USB. And then the same thing is when the actual output from the RAM, which we'll have to read with the Raspberry Pi Pico, it ended up being that the output was 3.3 volts too. I don't know if that's because it matched the input or what. I did not look at how the circuit works internally on this static RAM, but I thought it would come out as a 5 volt, and then I would have to level it down to a 3.3, but I didn't have to do that. I didn't have to do anything special. So anyway, now we need to actually look at the data sheets, the pinout for the Raspberry Pi Pico, as well as the static RAM. And for every address line, we're going to have to run that back to one of the Raspberry Pi's GPIO lines. So, all these green ones are GPIO lines that we can use. So basically, for each address line, A0 through A7, run a jumper wire back to one of the GPIO pins, one of those green rectangle pins on the Raspberry Pi. And we'll have to note that down which one it is. There's GP0 is going to be what's called pin 0. GP1 will be pin 1. GP2 will be pin 2, even though it's actually physically pin 4, and so forth and so on. Then we'll have to wire not S2 and not S3, that is pins 4 and 5, to the ground, as well as pin 8 to ground. And we'll have to wire pin 16 to our plus 5, which is going to be V bus on the Raspberry Pi, pin 40, and then we'll have to wire ground from pin 38, ground on the Raspberry Pi, to all those ground points that we mentioned. We will also have to wire pin 3 on the RAM, which is not S1, to one of the GPIO outputs, and we'll have to wire pin 13D to a GPIO pin. That's going to be the data into the chip. Pin 12 also, read not write, has to go to a GPI pin, an output pin. And then pin 6 is the actual output from the RAM, which we're going to have to run to a GPIO pin, and then actually that pin has to be configured as an input. All the other pins will be outputs. Finally, we're going to have 3 lights on the device that will allow us to see visually if the 3 tests pass. So on 3 more of the GPIO pins, the green pins on the Raspberry Pi, we have to configure them as outputs. Configure, for each pin, plug in a 400 or so, 440 in the case that I use, that's what I had, ohm resistor, and then a LED. And the LED positive side has to go towards the resistor near the Raspberry Pi, where the other end goes into ground. And those will be our lights. Once we have it all wired up, it should look something like this. And now we just need to program it. Okay, so we pull up Thani, which is an easy to use tool that lets us install MicroPython and gives us an IDE to the Python language. Lets us load it into the Raspberry Pi. And so obviously we're going to import this machine, we're import random, and we're going to do from time import star. I don't know why I didn't from whatever import star the other ones, but whatever. And then what we have to do is layout. This is very important. You got to get this right. For every pin you chose, whatever the pin number was, create a variable A0 for address line 0 equals machine pin, whatever GPIO pin you use. Like I use 0 for A0. And then you want to make it machine pin out. All these pins except for 1, the data in, is going to be out. So you basically just map them to whatever way you plugged them into the Pi. Then these test 1, 2, and 3 is actually our LEDs. I should call them LED 1, 2, and 3. But same thing. Whatever pins you plugged basically those resistors into and the LEDs, just map them the same, give them a name, test 1, 2, and 3, machine, pin, whatever number it was, and then out. Okay. And then what I do is I immediately set those values to 0 so the light is off when the thing starts. And then we still have a couple more pins. We have the read not write pin, and that's going to be machine pin whatever you chose, again an output. CS for chip select, and again whatever, it's going to be an out and whatever pin you did. Data out, and again whatever pin you wired up to basically the data in pin, the D pin, which I think was pin 13. And then finally D in, and that's going to be whatever pin was pin 6 on the RAM. Now the only difference is this one's going to be configured as pin in, because we will actually read that back to verify. Okay, so we define all our pins, then we turn off the test LEDs, and actually I could have defined I could have done the turn-offs after it. I probably should have. And then we turn off the chip select. And by turn chip select off, we actually have to set it high. And then all we have to do is write some code to read the RAMs, write to the RAMs, and toggle the control pins, the read not write. So when we want to set read, we set that high, because that's what read is. When we want to write, we have to set it low. And then the chip select, enable and disable. Again, to enable it, we actually set it low. And to disable it, we set it to high. And I have a function to set the address, basically because we have to do that for when we go to set the address, we have to set all the address lines. Then we just have to make sure we have to look at the data sheet and see how the timing happens. And basically to read a value, the chip should be disabled. Then we're going to put the address on the address lines, set the read option to read, which is high, and then turn on the chip select, which is enable. And then the value we read, we're going to look at the input value, DIN value, and it's going to be the opposite because the chip, when it outputs, the RAM, when it outputs the data, it's going to be the opposite of the actual value stored. And that's in the data sheet. It says the chip pin 6 says it's a complement or the opposite of whatever the actual data stored was. And then the write value, the timing is, again, we disable it, set the address, set the value that we actually want to write, and then tell it to write and enable it. Okay. And then I make a test. My test is very simple. It basically creates an array, fills it with either zeros, ones, or all ones, all zeros, or random. And then it writes all the values, the all zeros, all ones, or then whatever random array it selected, and then it reads it back and makes sure that every value is the value that we wrote. And if it passes, we say pass, and we return true. Otherwise, we print false and return false. And then we, depending on the values of the test, we set the lead for that test. So, and then I just sleep a second just so it's easier to read. You don't actually even have to do that, but I do. And the test function handles all of them, whether it's all zeros, all ones, or random. And we choose which value we want, whether we want to run all zeros or all ones by choosing true, false, or none. True means it's going to be all ones. False means it's going to be all zeros. And none means it's going to be random. Okay, let's give it a shot. Nice.